The morning of August 12th, 1944. A dirt road outside the Norman village of Cintho, France. Sergeant Robert Hayes of the 2nd Armoured Division crouched behind a hedgerow, binoculars pressed to his eyes, watching something that should not have been possible. 50 metres ahead sat a German Panzer tank, engine silent, crew gone, hatches open. The massive machine tilted slightly to one side, its right track thrown from the drive sprocket, lying in the mud like a shed snakeskin. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Hayes had been briefed about the Panther. Intelligence called it the most dangerous tank in the German arsenal. Sloped armour that could deflect 75mm shells at any range. A gun that could destroy a Sherman from 2,000 metres away. A technological marvel that represented everything. Allied tankers feared about German engineering superiority. Yet here it sat, abandoned not because American guns had destroyed it, but because something inside the machine had simply broken. The crew had walked away, leaving Germany's finest weapon sitting useless beside a French country road. This was not the first abandoned Panther that Hayes had seen in the 2 months since D-Day. In fact, abandoned Panthers had become disturbingly common as American forces pushed inland from the Normandy beaches. Tank after tank, sitting in fields and along roadsides, hatches open, crews vanished. Some showed battle damage, certainly, but many appeared mechanically intact from the outside, their thick armour unmarred by shell impacts. Something was systematically destroying these machines from within. The intelligence officers were desperate to understand what was happening. Were the Panthers really as invincible as German propaganda claimed, or did these abandoned tanks reveal a fundamental weakness that could be exploited? The answers would come from systematic examination of captured vehicles, from technical teams crawling through every component, documenting every failure, building a comprehensive picture of what was actually defeating Germany's most advanced tank. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Panther emerged from Germany's shocked response to encountering the Soviet 34 in the summer of 1941. German forces advancing into the Soviet Union expected to face obsolete equipment operated by poorly trained crews. Instead, they encountered a tank that combined sloped armour, a powerful 76mm gun, wide tracks for superior mobility, and mechanical simplicity, into a design that rendered German Panzer III and Panzer IV tanks obsolete almost overnight. The impact was immediate and profound. German tank commanders who had dominated Poland and France suddenly found themselves outgunned and outmaneuvered. The 34's sloped armour caused German anti-tank shells to deflect harmlessly. Its wide tracks allowed movement through mud and snow that bogged down German vehicles. Its diesel engine was both more fuel-efficient and less prone to fire than German gasoline engines. Most disturbing of all, Soviet factories were producing these superior tanks in quantities that Germany could not match. In November 1941, the German Army Weapons Department issued specifications for a new medium tank to counter the Soviet threat. The design competition between Maschinenfabrik Augsburg-Nürnberg, commonly known as MAN, and Daimler-Benz resulted in MAN's design being selected in May 1942. Production began in January 1943 with the OSF-D variant, followed by the OSF-A from August 1943 and the OSF-G from March 1944 through war's end. The specifications were impressive on paper and represented genuine advances in armour, design and firepower integration that German engineers believed would restore battlefield superiority. Combat weight of 45 metric tons placed the Panther between American medium tanks weighing 30 tons and German heavy tanks like the Tiger I weighing 57 tons. This intermediate weight class was intended to provide heavy tank capabilities with medium tank mobility and production cost, creating a weapon that could be deployed in sufficient numbers while maintaining technical superiority. Frontal armour of 80mm, sloped at 55 degrees from vertical, provided protection equivalent to approximately 140mm of vertical armour. through the principle that sloped armor increases effective thickness relative to the projectile impact angle. This sloped armor design, copied directly from the Soviet 34, represented a significant advance over earlier German tanks that used vertical armor. Side armor of 40 mm provided adequate protection against light anti-tank weapons and autocannon fire, but remained vulnerable to all Allied tank guns and medium anti-tank guns at combat ranges. The main armament, a 75 mm KK-42 L-70 gun, represented the most powerful tank-mounted weapon in widespread service during 1943 and 1944. The designation L-70 indicates that the barrel length was 70 times the caliber, providing the extended barrel length necessary for high muzzle velocity. Muzzle velocity of 925 meters per second with standard armor-piercing ammunition provided penetration capability exceeding any Allied tank gun through 1944. At 1,000 meters range, the gun could penetrate 120 millimeters of armor, sufficient to defeat any Allied tank frontally. At 2,000 meters, penetration remained adequate to destroy Shermans through frontal armor, while Sherman guns at the same range could not reliably penetrate Panther frontal armor. This enormous advantage in effective engagement range gave Panthers the theoretical capability to destroy enemy tanks before coming under effective return fire, exactly the fundamental principle of German tank gunnery doctrine. The Maybach HL-230P30 engine represented sophisticated German automotive engineering applied to military requirements. This water-cooled 12-cylinder gasoline engine, mounted in a 60-degree V configuration, displaced 23.1 liters and weighed 1,200 kilograms. Maximum output of 700 metric horsepower, equivalent to 690 imperial horsepower, occurred at 3,000 revolutions per minute. Normal operational output was 600 metric horsepower at 2,500 revolutions per minute, to reduce wear and extend engine life. This power output provided a power-to-weight ratio of 15.6 horsepower per ton, comparable to medium tanks of similar weight. However, the engine consumed high-octane gasoline requiring 74 octane minimum for reliable operation, a fuel grade that Germany struggled to produce in adequate quantities from synthetic fuel plants as the war progressed, and access to petroleum reserves became increasingly constrained by Allied advances and strategic bombing campaigns. The AK-7200 transmission represented advanced engineering that provided capabilities exceeding most contemporary designs. 7 forward speeds allowed optimal engine speed selection for various terrain and tactical conditions. 1 reverse speed provided retreat capability, though reverse speed was limited compared to forward speeds. The transmission was designed to handle the power output of the Maybach engine under normal operating conditions. However, and this would prove catastrophic, the 45-ton combat weight exceeded original design parameters, placing stress on transmission components that contributed to premature failures. Transmission oil overheating was a persistent problem, particularly during extended cross-country movement or combat operations requiring frequent speed changes and high power output. Oil cooling systems proved inadequate for sustained high-stress operation, leading to thermal breakdown of lubrication and rapid wear of internal components that would ultimately cripple Panthers across every theatre where they deployed. Maximum road speed of 46 km per hour provided tactical mobility comparable to other medium tanks. Cross-country speed of approximately 25 km per hour under favourable conditions gave the Panther adequate mobility for exploitation operations when mechanical reliability permitted sustained movement. Operational range of 260 km on roads assumed optimal conditions with proper repairs, maintenance and careful fuel management. Cross-country range of approximately 100 kilometers reflected the dramatically increased fuel consumption and mechanical stress of off-road movement. Fuel capacity of 730 liters required frequent refueling during sustained operations, creating logistics demands that German supply systems struggled to meet, particularly as Allied air superiority increasingly disrupted German fuel transport networks. Road fuel consumption of 2.8 litres per kilometre meant that a 100-kilometre road march consumed 380 litres, requiring more than half the fuel capacity. Cross-country consumption of 7.3 litres per kilometre meant that cross-country movement consumed the entire fuel load in approximately 100 kilometres, exactly matching the specified cross-country range. These specifications made the Panther theoretically superior to any Allied tank in service during the summer of 1943. The sloped frontal armour could defeat hits from American 75mm guns at all practical combat ranges. The long-barreled 75mm gun could destroy Sherman tanks at ranges exceeding 2,000 metres, far beyond the effective range of Sherman return fire. British armour commanders in Normandy would describe the Panther as the finest tank in the European theatre, based purely on armour and firepower specifications. German propaganda celebrated the Panther as proof of Aryan technical superiority, a weapon that would restore German dominance on the Eastern Front and repel the inevitable Allied invasion in the West. Newsreels showed Panthers rolling off factory floors, their massive guns traversing smoothly, their thick armour gleaming under camera lights. The message was clear and confident. Germany had answered the Soviet 34 with an even better tank that would demonstrate once again that German engineering excellence would overcome any obstacle, any challenge, any enemy. The reality revealed itself immediately at Kursk in July 1943, in what would become the largest tank battle in history. German official reports documented the collapse with mathematical precision that shocked German military leadership and validated Soviet claims that German propaganda had dismissed as impossible exaggeration. The numbers told a story of catastrophic failure that no amount of propaganda could conceal or explain away as temporary setbacks. It was not until June 23 through June 29, 1943, that a total of 200 rebuilt Panthers were finally issued to Panther Regiment von Lauchert of the WWII Panzer Corps attached to 4th Panzer Army. 2 Panthers were immediately lost to motor fires on disembarking from the trains, burning before they even reached German assembly areas. The regiment had spent the intervening week conducting final preparations, minor repairs, and crew training on the new vehicles. Morale was high despite concerns expressed by experienced maintenance officers who recognized that the Panthers had not undergone adequate durability testing. Tank commanders who had fought in earlier Panzer III and Panzer IV tanks praised the Panthers' superior armour and firepower, believing these advantages would prove decisive in the coming offensive. These hardened veterans expected to smash through Soviet defences with ease, their new weapons finally providing the technological edge that would reverse German fortunes on the Eastern Front. By July 5, 1943, when the Battle of Kursk started, only 184 Panthers remained operational after additional mechanical failures during the short journey to forward positions. The first day of combat revealed problems immediately that shattered German confidence in their new weapon. By July 7th, after just 2 days of combat operations, only 40 Panthers remained, operational from the original force of 184 that had entered battle. This catastrophic 65% loss rate occurred primarily from mechanical breakdown rather than enemy action, a fact that German after-action reports documented with bureaucratic precision that could not hide the magnitude of the disaster. Final drives failed under the stress of cross-country movement through muddy terrain, transmissions overheated and seized, their internal gears stripped by loads they were never designed to carry. Engines caught fire from fuel system problems that inadequate testing had failed to identify. Cooling systems leaked, causing engine overheating that led to catastrophic failures requiring complete engine replacement. Tracks broke under the strain of the 45-ton combat weight, leaving Panthers immobilized in the middle of battlefields. Suspension components fractured from terrain impacts that lighter tanks would have absorbed without damage. German maintenance units, overwhelmed by the volume of failures and lacking adequate spare parts, because production had focused on building new tanks rather than stockpiling replacement components, could not repair disabled Panthers fast enough to maintain operational strength. The German report dated July 20th, 1943, compiled after the offensive had clearly failed and German forces were withdrawing, and confirmed the extent of the disaster with bureaucratic precision that made the failure impossible to dismiss or minimize. 41 Panthers remained operational from the original 200. 85 were repairable by regimental-level maintenance, if spare parts and time were available, which they increasingly were not. 16 required repair in Germany because damage exceeded field maintenance capability. 56 had burned out from enemy action. 2 had been destroyed by motor fires unrelated to combat. The operational rate at end of July was 16%, a figure so catastrophic that it triggered immediate investigations into what had gone wrong. Adolf Hitler personally demanded explanations, leading to investigations that blamed inadequate testing schedules and rushed production timelines rather than the fundamental design contradictions that actually caused the failures. The investigations sought scapegoats rather than systematic understanding, exactly the wrong response to a systemic engineering problem. The pattern established at Kursk repeated across every theatre where Panthers deployed throughout the war, suggesting that the problems were not isolated incidents but fundamental flaws in the basic design. Operational availability rates, defined as the percentage of tanks actually available for combat on any given day rather than undergoing maintenance or awaiting spare parts, averaged between 35 and 40% throughout 1943. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. German records compiled after the war show 37% average availability at end of 1943 across all theatres. This meant that a Panther battalion nominally equipped with 96 tanks could expect approximately 35 tanks actually operational on any given day. The remaining 61 tanks were either undergoing maintenance, awaiting spare parts, awaiting transport to repair facilities, or disabled in forward areas awaiting recovery. This availability rate made sustained offensive operations impossible because operational strength declined throughout any extended operation as mechanical failures accumulated faster than repairs could be completed. While these rates improved somewhat in 1944 to approximately 54% average, Panthers never achieved the reliability necessary for sustained offensive operations that German doctrine required, that had produced such stunning victories in Poland and France years earlier. Some periods showed better performance that reflected improved crew training and established supply chains rather than fundamental design improvements. September 1944 Eastern Front records indicate 75.8% availability, with 552 operational of 728 total. The Battle of the Bulge in December 1944 showed 71.3% availability, with 336 operational of 471 total. These improved figures, while better than earlier performance, still fell short of the 80 to 90% availability rates necessary for sustained offensive operations, according to German pre-war planning assumptions that had shaped entire strategic concepts. More importantly, these higher availability rates required extensive preparation, well-stocked supply depots, and favourable conditions that became increasingly rare as Allied pressure intensified and German logistics collapsed under the combined weight of strategic bombing, fuel shortages, and the simple impossibility of maintaining supply lines across multiple fronts while losing territory month after month. The comparison with Sherman operational availability reveals the cumulative impact of reliability differences that would ultimately prove decisive in determining which side could sustain offensive operations. While precise documentary confirmation of Sherman availability rates has not been located in all accessible sources, multiple authoritative analyses describe the Sherman as having superior reliability and superior mechanical reliability compared to the Panther. The operational reality visible in unit after-action reports and divisional strength summaries consistently shows American armored divisions fielding higher percentages of their authorized tank strength than German Panzer divisions throughout 1944 and 1945. This availability differential, approximately 30 to 45 percentage points favoring American forces, compounded the already substantial American advantage in total production numbers to create battlefield superiority that German tactical skill and technical specifications could not overcome. The core problem lay in a fundamental design contradiction that no amount of field modification could fully solve. The Panther was conceived as a 35-ton medium tank, but the addition of heavy armor and a powerful gun increased combat weight to 45 tons, a 28% overload. This weight exceeded the design parameters of virtually every mechanical component, creating cascading reliability problems that manifested in every system from the transmission to the final drives to the suspension. The most catastrophic failure point was the final drive, the mechanism that transferred power from the transmission to the drive sprockets that moved the tracks. The French Army provided the most comprehensive post-war analysis of Panther reliability through direct operational experience. France operated a full battalion of 50 Panthers through 1947 as part of the 503rd Tank Regiment, giving French forces almost twice as much operational time with Panthers as any German formation had achieved during the war. The official French Ministry of War report, titled Le Panther, published in 1947, stated explicitly that the truly weak spot of the Panther is its final drive, which is of too weak a design, and has an average fatigue life of only 150 kilometers. French examination of abandoned Panthers found in Normandy in 1944 revealed that half showed evidence of final drive failures. This was not combat damage, but mechanical failure from normal operation under field conditions. The metallurgical analysis conducted by French and American technical teams after the war revealed the underlying cause that explained why German final drives failed so consistently and catastrophically. German steel production in 1944 reached 28.5 million tons through incorporation of conquered territories, including French Alsace and Czech Sudetenland. Production had peaked at 34.6 million tons in 1943, before declining as Germany lost access to critical resources. However, Germany had lost access to critical alloying metals necessary for high-quality steel production, metals that were essential for components subjected to extreme stress. Allied bombing of the Carnarvon molybdenum mine in Norway in 1943 eliminated Germany's primary source of this critical element. Molybdenum increases steel's resistance to heat and fatigue, exactly the properties needed for final drive components operating under continuous high stress. Nickel, another critical alloying element, essential for creating steel with the necessary strength and durability, became increasingly scarce as the war progressed, and Germany lost access to international markets and foreign sources. Soviet technical trials of captured Panthers found armor plates containing between 0.6 and 1.7% nickel in various locations, suggesting significant variation in material quality depending on when and where components were manufactured. German sources described final drives as made of low-grade steel with low core strength of material used. While the specific percentages of deficiency could not be verified in all accessible primary sources, the general material degradation is extensively documented across multiple independent analyses by American, British, French and Soviet technical teams examining captured vehicles. The combination of design overload and material quality decline created a catastrophic reliability problem that no amount of crew training or careful preparation could overcome. Final drives that should have lasted thousands of kilometers under normal conditions failed after as little as 150 kilometers of operation. Transmission failures, engine problems, and suspension damage occurred at rates far exceeding those of Allied tanks, creating a cumulative disadvantage that shaped every campaign where Panthers deployed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The production statistics tell the story of Germany's strategic error with mathematical precision that reveals the true cost of pursuing technical perfection over practical reliability. Germany produced approximately 6,000 Panthers between January 1943 and April 1945. The breakdown by variant shows 842 OSF-D from January to September 1943, 3,400 OSF-A from August 1943 to August 1944, Approximately 2,961 Ausfuhr G from March 1944 to April 1945, plus 329 Befehlspanzer command variants. Peak frontline strength reached 2,304 tanks on September 1, 1944. Production cost per Panther was 117,100 Reichsmarks without armament and radio, compared to 250,800 Reichsmarks for the Tiger I and 103,462 Reichsmarks for the Panzer IV. The Panther occupied an uncomfortable middle position in cost, significantly more expensive than the proven Panzer IV, but not delivering the overwhelming combat power of the Tiger I. The United States produced 49,324 Sherman tanks in 11 plants between February 1942 and July 1945, representing the most successful tank production program in military history, measured by total units produced and sustained over time. The Sherman, officially designated M4 medium tank, evolved through multiple variants using different engines, transmissions, and hull configurations, while maintaining commonality of critical components that simplified logistics and maintenance to a degree German planners could never achieve. The most common variant used the Continental R975 radial engine, producing 400 horsepower, licensed from the Wright R975 Whirlwind aircraft engine. This 9-cylinder air-cooled radial engine, originally designed for aircraft, proved remarkably reliable in tank application, despite initial skepticism about adapting aircraft engines to ground vehicles. The Sherman weighed 30 metric tons in combat configuration, 15 tons lighter than the Panther. This lower weight reduced stress on all mechanical components, improving reliability and extending service life in ways that compounded over thousands of vehicles and millions of operational kilometers. The main armament on most Shermans was a 75mm M3 gun, a competent weapon adequate for destroying most Axis tanks through 1943, but increasingly inadequate against heavily armoured German tanks like the Panther and Tiger from 1944 onward. Maximum armour of 76mm on the frontal hull, mounted vertically rather than sloped, provided less protection than Panther armour but proved adequate against most German tank guns at medium ranges. Maximum road speed of 40 km per hour, slightly slower than the Panther, provided adequate tactical mobility for American armoured doctrine that emphasized sustained operations over maximum speed. The Sherman's true superiority lay not in specifications that could be written on paper and compared in charts, but in reliability, maintainability, and production efficiency that determined what actually appeared on battlefields. The Continental R975 engine required minimal maintenance compared to the complex Maybach engine in the Panther. Oil changes every 250 hours of operation versus every 100 hours for the Panther reduced maintenance burden significantly. Air cooling eliminated the complex cooling system that plagued Panther operations, removing an entire category of potential failures that had immobilized hundreds of German tanks. The transmission, though less sophisticated than the Panther's 7-speed design, proved remarkably reliable and could be replaced in field conditions within 8 hours by trained maintenance crews using standard equipment. Final drives, conservatively designed with adequate strength margins for the Sherman's weight, rarely failed under normal operating conditions. Suspension components using vertical volute spring bogies instead of interleaved road wheels could be maintained and repaired quickly, without extensive disassembly. This seemingly mundane engineering choice had profound operational consequences. A Sherman crew could change a damaged road wheel in 30 minutes. A Panther crew might need an entire day to change an inner road wheel, because the interleaved design required removing multiple outer wheels first, assuming they had the specialized tools and equipment necessary for the job. Production efficiency gave the Sherman overwhelming numerical advantages that shaped strategic possibilities across multiple theaters simultaneously. The average Sherman required approximately 10,000 man-hours to produce in established factories operating at peak efficiency by 1944. The Panther required approximately 15,000 man-hours, 50% more labor for each unit, labor that Germany increasingly could not spare as manpower shortages intensified. American factories used advanced production techniques including extensive subassembly, standardized components across variants, and progressive assembly methods that minimized skilled labor requirements and allowed rapid scaling of production. German factories relied more heavily on skilled craftsmen to fit components that were less precisely standardized, increasing production time and costs while creating bottlenecks that limited total output. American production peaked at over 2,000 Shermans per month during mid-1944. German Panther production peaked at approximately 380 units per month, less than one-fifth of American output, despite Germany dedicating proportionally more industrial capacity to tank production. This production differential meant that even if Panthers and Shermans were equally reliable, which they demonstrably were not, American numerical superiority would still prove overwhelming. The operational consequences of these production differentials compounded over time in ways that shaped strategic possibilities. American armored divisions that suffered tank losses in combat received replacement vehicles within weeks, sometimes within days if supply lines were functioning normally. Crews knew that destroyed tanks would be replaced, reducing psychological stress and encouraging aggressive tactics that accelerated the tempo of operations. German Panzer divisions that suffered losses waited months for replacements, if they received any at all, as production struggled to keep pace with losses across multiple fronts. Crews knew their Panthers were irreplaceable, creating caution that undermined German tactical doctrine requiring aggressive action and rapid exploitation of tactical success. By late 1944, many German Panzer divisions operated at less than 50% authorized tank strength, not from combat losses alone, but from inability to replace losses at rates matching attrition. Yet the Sherman won the war, while the Panther lost it, precisely because specifications written on paper matter far less than availability on the battlefield when combat is actually joined. The fundamental principle that determined victory was not which tank had better armor or firepower in theoretical comparisons, but which tank was actually present and operational when needed, where needed, for as long as needed to complete operational objectives. The maintenance burden imposed by the Panther consumed resources Germany could ill afford as the strategic situation deteriorated month by month. Each Panther battalion required specialized recovery vehicles, mobile workshops, and stocks of spare parts that dwarfed the logistics footprint of a Sherman battalion. A typical American armored division required approximately 200 trucks dedicated to armored vehicle maintenance and supply. A German Panzer division equipped with Panthers required approximately 400 trucks for the same function, trucks that Germany did not possess in sufficient quantities and could not fuel even if possessed as petroleum stocks dwindled. The fuel consumption differential compounded the problem in ways that limited German operational planning. A Sherman battalion conducting a 100-kilometer road march consumed approximately 14,000 liters of gasoline. A Panther battalion conducting the same march consumed approximately 35,000 liters, assuming all vehicles completed the march without mechanical failure, which historical records suggest was increasingly unlikely as the war progressed. By late 1944, Germany was producing approximately 6 million tons of synthetic fuel annually, barely one-tenth of American petroleum production. This fuel shortage constrained German operations more severely than any other single factor. The psychological impact on German forces of their supposedly superior equipment's mechanical fragility emerges clearly from captured documents and post-war interviews with surviving crew members. German tankers learned through bitter experience that their Panthers were unreliable in ways that threatened their survival. The knowledge that their vehicle might break down at any moment, stranding them deep in enemy territory far from recovery assets, created caution that undermined the aggressive exploitation of tactical success that German doctrine required for victory. Commanders hesitated to commit Panthers to bold maneuvers because they feared mechanical failure more than enemy fire, a psychological burden that tactical manuals had never anticipated. This psychological burden, imposed by flawed engineering, contributed to German tactical paralysis during the final year of the war, as officers who had once led aggressive armoured thrusts now hesitated to commit their dwindling forces to operations where mechanical failures might prove as deadly as enemy action. The Battle of the Bulge in December 1944 demonstrated these problems at operational scale in Germany's last major offensive in the West. German forces committed 471 Panthers to the offensive, with 336 operational at start, a 71% availability rate that represented exceptional preparation possible only through weeks of careful maintenance and stockpiling of spare parts. Within 1 week, mechanical failures had reduced operational strength by approximately 1/3, not from combat losses, but from breakdowns during the advance through the Ardennes. Panthers abandoned for mechanical reasons littered the roads through the region. German recovery units, already stretched thin, could not retrieve all disabled vehicles before American forces recaptured the territory. The offensive failed not primarily from lack of fuel, as popular accounts suggest, but from the systemic unreliability of German armoured vehicles that limited operational tempo even when fuel was available. The contrast between German and American approaches to military technology extended beyond tanks to virtually every category of equipment in ways that revealed fundamentally different philosophies about industrial warfare. German small arms were magnificently engineered but expensive and slow to produce. The MP-40 submachine gun required approximately 10 hours of skilled machinist time to manufacture. The American M3 grease gun required less than 3 hours of semi-skilled labor. Both weapons fired the same caliber ammunition at similar rates. The American weapon was uglier, cruder, and vastly more practical for mass production in factories operating around the clock. This pattern repeated across artillery, aircraft, vehicles, and every category where American pragmatism confronted German perfectionism. The philosophical difference reflected fundamentally different understandings of modern industrial warfare, shaped by different historical experiences and different strategic circumstances. German military culture, rooted in Prussian traditions, emphasizing individual excellence and technical sophistication, could not adapt to the reality that 20th century warfare rewarded mass production over individual perfection. The German army entered World War II with doctrines developed from World War I experience, emphasizing breakthrough and exploitation through concentrated armored formations, employing technically superior equipment operated by highly trained elite forces. This doctrine achieved spectacular successes in Poland and France against enemies who were unprepared and poorly organized. Against the Soviet Union and the United States, nations capable of absorbing initial defeats and mobilizing vast industrial resources, the German approach failed catastrophically. American military doctrine, informed by different historical experience and different industrial capacity, embraced mass production and logistical sustainability as primary virtues that shaped every procurement decision. The Sherman tank exemplified this philosophy completely. It was not the best tank by any specification. It was the best tank that American industry could produce in sufficient quantity, that American logistics could support in global operations across multiple theaters simultaneously, that minimally trained crews could operate effectively after abbreviated training periods, and that field maintenance units could keep operational under combat conditions. These virtues, dismissed by German engineers as evidence of technical inferiority and lack of engineering sophistication, proved decisive in determining which side could sustain multi-year campaigns across continents. The final accounting reveals the magnitude of Germany's strategic error with mathematical certainty. 6,000 Panthers hamstrung by mechanical unreliability achieved operational effectiveness roughly equivalent to 3,000 reliable tanks when availability rates are properly considered. The resources consumed by Panther, production could have produced approximately 9,000 Panzer IV tanks. The Panzer IV, while inferior to the Panther in specifications, was mechanically reliable and adequate for combat against all but the heaviest Allied armour. 9,000 Panzer IVs, actually available for combat rather than awaiting maintenance, would have provided far greater military value than 6,000 temperamental Panthers. This conclusion is not speculation, but mathematical certainty derived from operational availability statistics and production cost analysis. The human cost of German over-engineering extended beyond logistics to training and doctrine in ways that consumed time Germany increasingly did not have. Panther crews required extensive specialized training to operate and maintain their complex machines. This training took months that Germany could not afford as the strategic situation deteriorated. Sherman crews could be trained to basic proficiency in weeks, allowing rapid expansion of American armored forces. The mechanical simplicity of the Sherman meant that crew survivability was higher because catastrophic mechanical failures were less likely to trap crews in disabled vehicles under fire. German tank crew casualties from mechanical failures that prevented escape from damaged vehicles were proportionally higher than American casualties from the same cause, though precise comparative statistics are difficult to establish from available records due to incomplete German documentation as administrative systems collapsed. The British Army's experience with captured Panthers provided additional confirmation of German reliability problems through independent testing under controlled conditions. British forces tested Panther No. 433, a mid-production OSF-A variant, in mobility trials in the United Kingdom during 1944. The British technical description of this specific tank was completed in late May 1944. British reports confirmed German findings about final drive weakness and noted additional problems with the interleaved road wheel suspension that German designers had implemented to improve cross-country performance. The overlapping wheel design, featuring wheels mounted on overlapping axles rather than individual bogies, provided superior weight distribution and ground pressure reduction in theory. This allowed the Panther to traverse soft ground more effectively than tanks using conventional suspension designs. The theoretical advantages were genuine and measurable in controlled testing conditions under ideal circumstances. The practical reality under combat conditions told a profoundly different story that revealed the gap between engineering theory and battlefield practice. Mud accumulated between the overlapping wheels during cross-country movement. In winter conditions, common across much of the Eastern Front and Northern Europe, this mud froze solid overnight. By morning, the suspension was locked, immobilizing the tank until crews could chip away the ice or wait for temperatures to rise sufficiently for melting. This process could take hours under favorable conditions, days under severe winter weather that characterized the Russian front for months each year. German tankers in Russia learned to avoid muddy terrain whenever possible, limiting their tactical flexibility to avoid suspension immobilization that could prove fatal. Maintenance requirements for the interleaved suspension exceeded those of conventional designs by an order of magnitude, consuming time and labor that could not be spared. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.